Okay, class. Good morning.
Good morning, sir.
Hello, students. Good morning.
Good morning, sir.
How was your GCQ?
Okay lang, sir.
It's okay lang, sir.
Okay, fine. So yesterday we already tackled about the determinants and the elementary operations, right?
Yes, sir.
Yes, sir.
So for your final activity,
Yes,
I will
sir.
be dividing you into
Yes, sir.
4 groups.
Yes, sir.
Okay. And each group, you will be going to report your assigned topic. And each member must report. Am I clear?
Yes, sir. Yes, sir.
And to know your group members, just open your email. Yes, email.
Yes, sir.
Because I already sent to you your topic and as well as your group number. Okay.
Yes, sir.
On our next
Yes,
meeting,
sir.
we'll be having your report.
Opo, sir.
Am I clear?
Yes, sir.
Okay, very good.
Yes po, sir.
So keep safe everyone and stay at
Opo,
home.
sir.
Class dismissed. Okay, good morning. Today is the day of your reporting. So are you guys ready?
Opo.
Okay, let's start with the group 1.
Good day. Today I'm going to discuss about determinant and elementary row operation. So determinant is a scalar value that is a function of the entries of the square matrix. It allows characterizing some properties of the matrix and the linear map represented by the matrix. In a particular, determinant is a non-zero if and only if the matrix is isomorphism. The determinant of a product of matrices is the product of their determinant. So determinant of a matrix is denoted as that close in open parentheses A. The following facts about determinant allow the computation using elementary row operation. If 2 rows added with all other rows remaining the same time, if determinant are added, that TA close in open parentheses equal T det close in open parentheses A, where T is constant. If the 2 rows of a matrix is equal, the determinant is 0.
Good day everyone, my name is Christopher Pibawik. I would like to discuss another example of our topics is all about determinants and elementary row operation. Determinants are defined for all squared matrix. They are in various interpretation in Herbert table. Example of this, we can calculate the determinant using cofactor expansion along the first row of A. Then simplify the result. We could also do the cofactor expansion along the second row.
Good day everyone. Our topic is about determinant and elementary operations. Some example about the simple solve of determinants. And this is an example of determinants is the 2 by 2 determinants. So first before we can find the inverse of a matrix, we need first learn how to get the determinant of a matrix. So this is the determinant, and so to find the A, we should use this term. So you can solve. So example, if B equals to so if B is 2, 3, 1, and 5, find B. So by applying this, so you should 2 times 5 minus 3 times 1. So 2 times 5 equals to 10. 3 times 1 equals to 3. So 10 minus 3 equals to 7. And that's it.
Okay, thank you, Group 1. Let's proceed to Group 2.
And now, let us topic about determinant. Determinant in linear and multilinear algebra, a value denoted bit alpha associated with a square matrix alpha and n rows and n columns. Determinants are the use in ascertaining whether the system of equations in n unknowns has a solutions. If B is an n times 1 vector and the determinant of A is non-zero, the system of equations AX is equals to B always has a solutions.
Good day everyone, I am RVJ Gapato. I am the second reporter of the topic Elementary Row Operation and Determinants. And we saw in the previous lesson how to use elementary row operation to find an equivalent row matrix that contains a row with all zeros, or at least one top triangle. This lesson examines how basic row operations affect the determinants, so we just need to compute this simpler determinants. In particular, this lecture deals in more detail with the theory of the process, mainly giving the theorems and proofs with a few simple examples. With all of this material, it can be mentally taxing. I have the more practical example of how do we do this in the next lesson. If you recall, there are three types of elementary row operation. Multiply a row by a zero scalar, swap two rows, and replace one row with the sum and scalar multiplier of another row. We shall see what effect each of these operations has on the determinant.
We have an example here, and we are asked to find its determinant. Using elementary row operation, we rewrite matrix A to the upper right triangular form. In order to do that, first we must interchange the first row to the second row. Next, in order to have the diagonal number equal to 1, we have to multiply negative 3 to the first row, then add it to the second row to produce a new second row. Then after that, we factored out negative 12 out of the second row. And also factored out negative 2 out of the third row. Then simplify the factored number. Now, since we have a triangular matrix, we can conclude the determinant is negative 24 times 1 times 1 times 1 is equals to negative 24.
Good day everyone! So since my group mates has been done discussing about our topic's definition and its differences, one of them also has been giving us an example about our topic, which is the elementary row operations and determinants. So to conclude with, all I can say that we always needed to remember that elementary row operations always affects determinants. Row operations don't change whether or not a determinant is zero. At most, they change the determinant by a non-zero factor or change its sign. So with this, if two rows of matrix are equals, the determinant is zero. And that's how elementary row operation affects determinants or vice versa. So we do hope that you were able to understand anything about our reporting. I'm Baby Jean Mag-Asobaran, your Group 2 last reporter. Thank you and God bless us all.
Okay, thank you, Group 2. And now let's proceed to Group number 3.
Have a good day everyone. We are tasked to report about determinant and elementary. Determinant, a function of a square matrix by multiplying and adding the elements together obtain a single number. The determinant of the matrix is a special number that can be calculated from a square matrix.
My task is to share to you what the importance of a determinant and elementary columns operations. The importance of determinant. Determinant is a useful for linear equation capturing how linear transformation changes area or volume, and changing variables, integrals. A determinant can be viewed as a function whose input is a matrix and whose output is a number. And the importance of elementary matrix operations play an important role in matrix algebra application, such as finding the inverse of matrix and solving simultaneous linear equations.
So now, I'm going to show you on how to find a determinant using an elementary column operations. So for example,
we have a matrix A is equal to negative 1, 3, and 5. Second column, 2, negative 6, and negative 10. Third column is 2, 4, negative 3. As you can observe, the first column of A are multiple of each other.
So, we can obtain a column of zeros by multiplying the first row into 2, then add it to the second row. So, I'll show you.
It is equal to negative 1 times 2 plus 2 is equal to 0. Next is 3 times 2 plus negative 6 is equal to 0. And 5 times 2 plus negative 10 is equal to 0.
So, we got now matrix A is equal to negative 1, 3, 5. Second row is the column of 0, which is 0, 0, 0, 2, 4, negative 3. We have now a column of 0, which is the second column. That's why we don't need to continue to rewrite the matrix in triangular form. Therefore, the determinant of matrix A is equal to 0. The validity of these conclusions follows from theorem 3.1.
Okay, thank you, group number 3. And now let's proceed to the last group, group 4.
Our task is to report about matrix and zero determinant. What does it mean to have a determinant of 0? If the determinant of a square matrix n by n A is 0, then A is not invertible. This is a crucial test that helps determine whether a square matrix is invertible if the matrix has an inverse. When it does have an inverse, it allows us to find a unique solution to the equation AX is equals to B given some vector B. When the determinant of a matrix is 0, the system of equations associated with it is linearly dependent. That is, if the determinant of a matrix is 0, at least one row of such a matrix is a scalar multiple of another. When the determinant of a matrix is 0, its rows are linearly dependent vectors and its columns are linearly dependent vectors also. Thank you and God bless.
Good day, sir. The example of the matrix conditions that negate a zero determinant. Given a square matrix, if an entire row or columns of the matrix consists of 0, for example, A is equals to 2, 5, 1, 0, 0, 0, 3, 4, and 2. Another example is 2 rows or columns are equal. For example, A equals to 8, 7, 8, 2, 3, 2, 4, 5, and 4. Thank you.
Example for the matrix with a zero determinant is that a bracket of numbers. Now I show you how to find a matrix using a zero determinant. Example, A equals to 1, 4, 1 for the first column and 2, negative 1, 0 in the second column, and 0, 18, 4 for the third column, and we have a matrix of A. The solution is by adding negative 2 times to the first column and add the second column. We have 1 times negative 2 plus 2 equals 0. 4 times negative 2 plus negative 1 equals negative 9, and 1 times negative 2 plus 0 equals negative 2. And we have the final numbers for the second column. Now we have a matrix of A equals to 1, 4, 1 in the first column, and 0, negative 9, and negative 2 for the second column, and 0, 18, 4 for the third column, and we have the matrix A. As you can observe that the second column and third column are multiple by each other. Therefore, the determinant of matrix A is 0 because the second column and third column are multiple by each other.
So, thank you for your cooperation. Thank you for your participation. And all of you got perfect score. You deserve that score. So, God bless everyone. Keep safe and stay at home. Goodbye. See you on our next meeting.